Okay, so for today, we will be doing some graph theory. Some very basic graph theory. So if you were in last year's senior class, then you probably know most of this stuff. I'm just going to sign into my Google account. All right. Let's create a REPL. And to this week is week 11. So we're finally in the double digits. Week 11 graph theory.
Wouldn't that mean we were in the double digits last week too? Because 10 is 2 digits.
Yeah, that's true. But, you know, we're still in the double digits. Alright, so we'll be doing some graph theory and some basic searching algorithms. And then after that, after I teach a little bit, today's going to be more of an independent work period. Which means that I'll teach the concepts, go over stuff with you, and then you guys will be solving the problems more on your own, but for like the remainder of the class. But I'll still be here if you guys have any questions or anything like that, and we might take up a question or two at the end. Okay, so graph theory, kind of a weird thing that usually in tradition, the senior class does dynamic programming, and then graph theory, and then after it's like CCC happens, then they go into some more data structures if they have time, or they prepare for competitions. But I felt like in recent years we didn't put enough emphasis on data structure, so I was teaching that first. So we put graph theory up until now, because unless you're new, most of you are probably familiar with some of the graph theory. It might just be a challenge to implement in C++, which is what I'm going to be doing. Okay, first off, let's go and make a poll. Are you familiar with BFS and DFS? Okay, so why the heck is the poll not working? Or am I just bad? Can people hear me?
Yep.
Alright, that's good. Did we just remove the poll spot? Okay. Alright, I'll manually put the reactions then.
It's offline, so.
Oh, that's unfortunate. Thumbs down. Alright, so go into the poll. Are you familiar with BFS and DFS? And remember, it's okay to say no, because I'm still going to go over anyways.
You should add a person shrugging emoji.
I should. Is that person shrugging or yeah? Okay, that's person shrugging. Don't want to be specific to any gender and use man shrugging or woman shrugging. I want to use person shrugging. Okay, so 11 people said yes. When if I can count, there's more than 11 people here. Okay, so for the sake of it, I'll assume most of you know graph theory in simple terms like a node and an edge. Okay, but let's have a look at this diagram that I started creating but failed to finish. Alright, and it looks really bad. So let me zoom in and create a better one. Okay, so let's say we have these nodes or vertices in some graph. And with the segment tree and everything we did, we were mainly looking at a graph with a certain amount of edges in a way that there's only one path between any two edges. Okay, so we have these four. Actually, let me just put these in a box. Okay, so here we have 4 nodes, 1, 2, 3, and 4, or vertices in the graph. And here we have 4 edges. The edge between 1 and 2, the edge connecting 1 and 3, the edge connecting 1 and 4, and the edge connecting 2 and 3. All right, so this is like a regular style graph, and the most basic graph that you'd have is if you can travel, you can go from 1 to 2 and from 2 to 1, which means that it's bidirectional. So you can, if you're a sitting passenger in a car, you could travel from 2 up to 1, but you also travel from 1 down to 2. Okay, and so that's a bidirectional graph. And then a unidirectional graph is, now let me get rid of the directions, is when you have each edge is only to one direction. So let's say I have 1 from 2 to 1. That was a really bad arrow. There we go. From 2 to 1. So if I was a sitting passenger, I could go up from 2 to 1, but I can't go down from 1 till 2 using that edge. And so I can assign certain directions here. And let's say I will make this one go here. And then this one goes over here. So you get the idea with the bidirectional and unidirectional nodes, unidirectional edges. So most questions I only use one type of edge instead of 2 types of edges, but I've yet to come across a question that uses both, or if not, if I have, I can't remember what it was. Okay, any questions with how I've drawn it up till now? Okay. So those are the basic terms. And now, let's get into some more complexity. All right. So we have 5, 6, 7. Actually, no, I don't want to, let me get rid of all these. I'm going to make a bunch of nodes that are unlabeled at first. Like, they're not labeled with numbers, but they're going to have boxes around them to signify that they're nodes and that they're edges that are connecting those nodes. Okay, so pardon me for this really horrible drawing that I'm doing. Take that out too. Okay. So the top of the tree, which we covered, if we're working with a tree, that's a graph. A tree is a type of a graph. So a tree is a graph. And the two characteristics of a tree are that if there are n nodes, there are n minus 1 edges. And with having n minus 1 edges, those edges are configured in a way such that there is exactly one path between each pair of nodes. And this is with the take that these edges are bidirectional. Okay, so there are 2 types of searching methods that we're going to cover. There are 2 types of searching methods that we will cover. Okay, does anyone know, or most people should know, does anyone want to say the first names of the 2 most common searching methods? All right, let me just call on someone.
I did not hear what you said there. Can you please repeat that?
What are the 2 types of searching methods in a graph? Kevin, how about you answer? I did not hear that.
Did I disconnect?
No, I just couldn't hear you.
Oh, okay. Breadth first search and depth first search.
Yes. BFS, which stands for breadth first search, and then DFS, which is depth first search. Not breadth first searching. All right, and there was also a joke that was rolled around about 2 years ago now, or two and a half years ago maybe. Brianna, what is the infamous nickname for breadth first search? Breakfast search. So this is just the reason that was that's a quote unquote
Breakfast
infamous
search.
nickname is because it was just a misunderstanding.
Yeah, your stream
Yeah,
is
it
dying
was
as
just
well.
cutting out a lot.
Yeah.
Okay, but I understood what she was saying. It's all right. It's because it was a misunderstanding of the name. Bread first kind of sounds like breakfast if you say it really fast. But that was a funny moment. I hope I'm not offending you, Brianna. Okay, so breadth first search. What is the idea of it? So the idea is that we want, like, what is breadth? And the idea that we use breadth first search is breadth here in this case means exploring or traversing through all edges or all nodes from a single point. And by doing that, what I mean is, let's say you started at the top of this tree 1. This is the first node that you visited. So then you look at all the different nodes that are under it, and you label them at, this would be the second node that you see, this would be the third node that you see, and this would be the fourth node that you see. And then you go into the first node, the first child that you looked at, and then you look at its children. So this would be the fifth thing that you see, the sixth, the seventh, and then from node 3, because that's the next thing in line, you go to the eighth. That's the eighth thing you see, and then you go in the line of the same breadth is the ninth thing you see. So if you kept expanding this downward, this would be 10, this would be 11, this would be 12, this would be 13. Kind of similar to the way we labeled the indexes of a segment tree, but not exactly, because there can be any amount of children of a node, or any amount of edges from a node, so not necessarily 2 edges. So we can't exactly say it's going to be labeled like that, but yeah. So notice how I said notice how I said putting all points in a line. In other words, a queue. And then so what you do is you add all the nodes that are connected to the current node, and then you add all these nodes to the current node in this line, and then you go to the next node or next labeled node in line. So that's the idea of breadth first search. And then depth first search, I had trouble saying. Depth first search is you're prioritizing depth this time. You're getting as deep as possible with one path. So what that would look like in this case is so if we go over here and take out all of these, and I'm only doing this so I can just get the labels. Alright, so the thing that you visit first will stay the same. So then you look at the children. Typically, I'm just going to label the children and go from left to right. So this would be the second thing that you see. But instead of, you label this as 2, but instead of labeling this node as 3, you go into the depth of this node, and you would go down and say, this is 3. And since this has no children, then you go back up here and say, go from 2 to 4. This is 4. And then you go 2 to 5. This would be 5. And then after, these don't have any children. These are empty. Like, they're quote-unquote leaves to their respective parent, if you want to call it like that. And then this one over here is fully used, so we can go on to the next child. So from 1, we go to this second child that has a value 6. Then you go into this thing's depth and this node's depth, and you go 6 to 7. And then so this is empty. So you're all good here. You're all good here. So now you have to go back into the third child, 8. And then lastly it'd be labeled 9. So notice the depth first search always prioritizes depth, while the breadth first search always prioritizes breadth. Or going widespread is breadth, and going downward is depth. So for every node connected, for every edge that connects to the node, we add those immediately and perform the and then traverse. We add those immediately to the stack, or not stack. Actually, yeah, we add those to the stack of edges or stack of nodes, and then move forward. So when I say stack, I mean in the sense of you push something in. Actually, let me just label this. A stack is some dash structure where you push from you push something from the front, and then you also take out from the front. So an example of that would be a pile of paper. So you put your first paper on top, and then its children. And you put the second paper is the child of the first paper, and then the third paper, and the fourth paper. And then when you remove, you take it out from the top as well. So that's what a stack is. Whereas the queue was the queue is taking from the front, but inserting from the back. This is a line. Lines are called queue, like a line in a grocery store even. These are typically called queues if you're trying to sound cool. So if you want a good synonym for line, then use queue in your essays. And yeah.
That makes sense, because if you're the last person to get in the queue, last.
I don't know if it was just me, but you cut out halfway and then I didn't understand the second half. But
Yes, I think he got out halfway.
It wasn't anything important, but I just said in the queue, like at the grocery store, if you're the last person, you're also the last person to get served.
That's true.
No way.
Especially with this global pandemic, now you have to actually wait outside grocery stores because there's a limited capacity on the inside. And crowded restaurants have always had this problem, where if they're too crowded, then they'd have to have a queue outside of their restaurant. But then again, there's reservations, which is essentially also adding on to the queue. But yeah, if you're entering last, but you're taken out before any of the people that were in front of you, you cut the line, and that's not allowed in graph theory. Why? Because it's not optimized. So C++ has a stack and a queue. So a queue, and then a stack. So let's just go into using the queue and a stack for a few minutes here. When you want to push to a queue, you just push some value. Like let's say we push 5, and then let's push a bunch of numbers here. And then how you would work it out is you keep going until the queue is empty. Because that means like you have no more things in line or like no more things to check. So let's say now I can store my value of the top element, or front in this case. So we take our integer x and that is queued up front. So that takes the element that's in the highest position, or that was entered first, that wasn't deleted. So and then if we printed x, this would happen. But if we just left it like this, let's run it. Is it even running properly? It's not compiling actually, so let me reload Replit. Okay.
Huh?
I can hear you, Kevin. I feel like his internet's just having difficulty.
You're not removing from the stack. You're not removing the queue at all. You have to pop it.
Exactly.
Try to pop.
All right. So I'm guessing I cut out there for like a good 10 seconds. Yeah, that's the problem. That's the issue here. With Python.
Oh, we couldn't hear you.
With Python, if I removed from the queue, I could do in Python. I can do x equals q dot pop, and it will return the value, and it actually assigns the value to x. But here, if I do q dot front, it won't return the value. But if it will return the value, but it won't delete it. But if I do q dot pop, whoops, it doesn't actually return anything. So you can't use q dot pop. So you have to use q dot front, and then after you have to pop it from the queue. Whoops, not q dot poop, q dot pop. So if we print it, we should see that we have 5, 6, 7, and 8. That's the exact order that we entered them in. Am I still cutting out, or am I good?
Is it just me, or is the stream frozen?
He's back now. Oh, he just got back.
Is the stream frozen, or am I am I cutting out?
The stream's okay, but sometimes you cut out,
Oh, gosh.
and the stream is frozen apparently.
That's not good. Okay. So now that we've learned how a queue works, let's see how a stack stores things. You can probably guess how it works, but we'll just do it anyways. So we can push a stack. We push 5, not stick. Stack.push. Let's put 10. Stack.push 25. And let's just put one more just for good measure. 58. Okay, and then here if we do not stack.empty, and then store the. Actually, we don't need to do that. We can just do cout stack dot. What is it? Stack.top. Very inconsistent. as you can see. But we're getting from the top of the stack instead of, because this is more like front of the line. This is like the top of your pieces of your pile of paper. So I guess it makes sense. So take the stack dot top, and then stack dot pop. We'll remove it. So if we print this out, we see that the 5, 6, 7, 8 was from here, and then we have 58, 25, 10, and 5, which is the exact opposite order of how we inserted them. So as we can see here, this is where the idea of that pile of paper and you take from the top every time comes in. That's logically how you take it from a pile of paper. Okay, so that's the idea of a queue and a stack, but there's something called a deck, which is annoyingly written as if it was called DQ. Like, there's no way someone would guess that's called deck, unless you're French. But with a deck, what you can do is actually, let's put some comments here. A queue is you take in from the back and then you remove from the front. So it's a LIFO. Last in, first out. A stack is a FIFO because it's whatever goes in first is what's also first to come out. And then a deck is all combinations of L and F. So what I mean is a deck is the most OP
Wait, what?
of the bunch.
Stack like last in first out?
Oh, am I cutting out? Can you guys hear me or no?
Yeah.
Alright. So a deck is the most OP of the bunch because you can add and remove in into the top and bottom. So let's go to see how this works. Push, and now we have these options. Push back and push front. Push back would push into the back of the line or back of the deck. Push front will push into the top of the deck. And then pop back would remove from the back, and then pop front would remove from the front. So add to back, add to front, remove from back, and remove from front. Okay, so then the question becomes, why do we use a deck, a stack, and a queue? The reason is insertion. Okay. We'll just work with the deck because it's got the same efficiencies as everything else. Insertion into the front or back of the deck is done in big O of 1. It's just one operation. Deletion from the front or back of the deck is also done in big O of 1. But the caveat here is and then accessing the front or back is big O of 1. So, but the reason we don't use an array for everything we do, for all of its purposes, the reason we don't use a deck instead of an array for all the array's purposes is because accessing an nth element in an array, in a deck, that is not the front or back has a efficiency is done in big O of n. So how it works really is if this was like a structure of like a struct of deck, how it's stored is you have a deck in the, or let's say you had a struct of a deck and then like some struct of a player, or let's say person in line. So struct person, how it's stored is you get person, you have a person in the back and a person in the front. And so insertions and deletions from the back and front are done really easily because all it takes is just modifying which person is behind a certain node and which person is in front of a certain node. There's no indexing here. And that's why if you try to index, it has to be done in big O of n, where n is the index of that thing in the deck. So if you've done, for the grade 12s, or for the people who have completed ICS4U or who have, I think, or like in progress at ICS4U, if you've done linked list and Mr. McKenzie made you like create a linked list from scratch, then you know pretty much all of this of a linked list. This is the equivalent of that. But if you don't know what a linked list is, don't worry about it. It's just a Java thing. And yeah, so this is a deck. So I recommend just using a deck for everything just because it has the benefits of both a stack and a queue. But if you know you're going to be using one and you don't remember if you had to push from the front, push from the back, take from the front, or take from the back, then you might be better off using the queue or stack, depending on if you use DFS or BFS respectively. Okay. So, those are the ideas of the different data structures you use to store, to traverse in the BFS or DFS methods. Now we'll go into the implementations. Okay. All right. So let's say we were given a graph, and let's say it had the edges. So let's just go off of this. So you had an edge from. Actually, let's label these as How do I want to label these? All right, let's just label them as 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's make a list of all the edges that are used. So we have an edge from 1 to 2, an edge from 1 to 3, an edge from 1 to 4, an edge from 2 to 5, an edge from 2 to 6, an edge from 2 to 7, an edge from 3 to 8, and an edge from 4 to 9. Okay. Alright, so let's just put these all in a comment over here. And let's do some implementations. So the data that we're going to use is all the edges. So we have unlock wasn't on. We have an edge from 1 to 2, an edge from 1 to 3, edge from 1 to 4, edge from 2 to 5, edge from 2 to 6, edge from 2 to 7, edge from 3 to 8, edge from 4 to 9. So those were our list of edges. And the way we could store, the way that you are best off storing these edges is with a vector, an array of vectors. So it would look something like this. Vector int graph and then some array size. Let's say 40. Okay, so let's take a look at why we use this. So the graph in this case is an array of vectors. The number of nodes is, or the maximum number of nodes is the array size. And then each node's vector is a list of, let's just say a list of all the edges that are connected to it, or all the nodes that are connected to it. Okay. So this is why we use a graph, or vector int of an array of vector ints. So that's the reason why we use that. So let's just enter these nodes, and I'll put a -1 over here. -1, -1. So you'll understand why I do that in a second. It's just so that I can take in edges easily. So this graph is initially empty. So now let's put some nodes inside of it. So while true, and then I'll take in some input. And then so int A and B, I'll just use A and B, where A and B are the two nodes that are connected. So while true, I'll take in A and B, and then I'll do if A is not equal to -1, or if A is equal to -1, I'll just break. So what I'm doing here is I'm just making my own input, so that if I input -1, then I'm just going to break from the function. I'm going to break from adding things to my graph, just so I don't have to manually stop it every time. I could use a for loop for the number of edges, but we'll just do it like this. So if A equals -1, then break. And then what we do is we go to our graph, then we go to index A, because we're working with our node A, and then we're going to push back B. So what this means is, now go to my go to the 8th element of index A in the array, and in that the array is a vector of all nodes that are connected to A. Now I'm going to add B to the list of nodes that are connected to A. And since I'm going to make this as bidirectional, if this was bidirectional, we have to do graph B dot pushback A. So this adds the A to the list of nodes that B is connected to. So we're taking our input with the edges, and then now let's do some BFS. So we still have our queue up here. We'll just use the queue. We'll just use the general queue, just because I don't want to get too confusing with the deck, but you can use the deck too. And we'll just do something simple, like printing out the list of the order in which we visit the nodes. So the queue is initialized. So what we do here is we push 1 to the list to the queue, and then we'll keep going until the line is empty, or the queue is empty. So this can be represented as while not queue.empty. Well, remembering that not is represented by an exclamation mark in C++. Or you can do while queue.empty equals false if you want to write it like that. And then what we do is we retrieve something from the top of the queue, just like we did up here. Int x equals queue.front. So int cur node equals queue.front. So this is the current element we are working with. And then, actually, let me just take this out for now. I'll just make it unidirectional, not worry about the bidirectional cases. But I'll go into that in a second. So if I take the current node, and let's just print out what the current node is. So cout current node \n, and then I'll add everything that's not in. I'll add all the nodes that are connected to A that are below A, or below this current node that haven't been visited yet. So for int I in graph at current node. So this is a special type of for loop. If you remember, you guys might know this from C++, or not C++, Java. But it's the same thing as for int for I in this list. So for int I in graph at current node, and we'll just push the next node. We'll push it to the queue. And now if we run this, and then input our data, and I made the same mistake as last time. I didn't remove the current element from the top of the queue. So they were labeled as 1, 2, 3, 4, 5, 6, 7, 8, 9, which means that I visited the nodes in the same order that they were numbered. And let's go back to our whiteboard. And this is, in fact, how I demonstrated that BFS would do it. It would go here, and then check this next, and then after check that, then it would go to each of the nodes' children and add those to the queue, and then so on and so forth. So those happen to be numbered in the exact same way. So that's BFS. Now DFS. DFS, we're going to be using the stack. By the way, can people still hear me?
I don't think you have cut out since.
Oh, that's good to hear. Okay.
That could be because I wasn't paying attention.
It's all right. If at any point I am cutting out, just feel free to shout out and let me know, so I know when to slow down and repeat something. Okay. So DFS, it's the same idea. We're first gonna push our first element to the stack, and then we still have our stack initialized, so we can do the same thing. While not stack.empty, let's take our current node, not front. This one is q dot. What do you call it? Q dot top. It's kind of goofy that they have this q dot top and q dot front, or not q, stack. It's kind of goofy that sometimes they have this stack dot top and q dot top. In hindsight, with stack and q, it makes sense, but it can get confusing, and it has caused me to have a lot of problems in my code before because I didn't think that I used one instead of the other, and it really messed me up for a long time once. So let's print our current node, and then we're going to do the same thing, except we're just adding it to our stack this time. So for int I in graph at current node, q stack dot push I. Okay. And then after, we'll do stack dot pop, just so we don't have any problems. So now when we run this and we enter in our data, which is up here, what happened? Why does 3 keep printing out? What? Where's 3 in the diagram? 3 is this node right here. Did it not process all the edges? Alright, I'll get ready. Alright, so I do have a problem in my code somewhere. Alright.
You're pushing the nose into the stack before you're popping. You're pushing its children into the stack before you're popping it out, which it works for a queue because it's first in, first out, but it doesn't work for a stack because you're just popping out the last guy.
Okay, yeah, he's got a good point there. Alright, so what happened was, the reason that 3 kept printing out was I was going over here and I was adding 2, 3, and 4 to the stack, but I was popping 4 instead of popping 1. And the reason was because I was adding all of them to the stack, and then I was adding all the nodes to the stack, and then I removed. So instead, I should have done stack.pop right up there. And that's a good point. It will work fine for a queue as well. If we put queue.pop here instead, it would run fine as well, instead of over there. So that's why in most situations, people just pop right after they access the node and have it stored somewhere, because then they don't have problems with stacks. So it'll work fine with queues if you have it below, but with stacks, since it's a FIFO data structure, then it won't, because of that, it won't work properly. So let's try running this again, and thank you, Kevin.
You're welcome.
And let's try adding these. Okay, I should probably not have this printing out, because it just gets confusing. Okay, so now we have this weird order, 1, 4, 9, 3, 8, 2, 7, 6, 5. And if we check with our whiteboard, so what happened here was, because I was adding from left to right, and my priority was left to right, that's why it was that's why it worked like this, where I went 2, 5, 6, 7, 8, 9. But because instead I was adding the nodes from, but since I'm not prioritizing doing left to right or anything like that, I'm just leaving it up to the computer. The stack had 1, and then 2, 3, 4, and then 1 got removed. And then the next thing in line, or the thing on top of the stack, was 4. Actually, no. I explained that wrong. Alright, I had 1 in the stack, then I removed it, then I added 2, 3, 4. So 4 is on top, so then I removed it and I added 9. And then I removed that. Then I went to this 3 over here, added 8, or I removed it and added 8, and so on and so forth. So that's why I had 1, 4, 9, 3, 8, 2, 7, 6, 5. And that the numbers over here, the numbers that you're seeing are complementing, are in the order, or not in the order, but the indexes that you're seeing over there are these red indexes. So that's why at BFS I was getting 1, 2, 3, 4, 5, 6, 7, 8, 9. Not because I was just listing the order of the nodes, but because the way I organized them and put them in the thing, it allowed it to just have to have the same indexes. But that's why that was listed as that. But that's why this is listed different. So if I wanted to do as 1, 2, 5, 6, 7, then 3, 8, and then 4, 9, I could reverse the order in which I visited the current node. So if I did instead for int I equals graph at current node dot size I is greater than or equal to 0, I minus minus, and then I push graph at current node at I, then it would happen, then the DFS would actually happen in order. Unless I made a mistake. Let's see. Or in the order of... Okay, so...
Shouldn't it be int I equals graph at kernel dot size minus 1?
Yeah, that's why. Of course that was typical me move. I always do that. So now I'm getting 1, 2, 5, 6, 7. Then I go to my next node, 3, and then 8, and then 4, and then 9. So that's the idea of BFS and DFS. And then using them so both of them can be used to find a certain node in a graph. But deciding on whether to use one or the other is it depends on the problem. So for a specific problem, one could be more efficient than the other, and then choosing which one to use is up to you. So this is the idea of BFS and DFS.